Okay, so our next speaker is Krista Hammond. She is Senior Content Manager for Space Weather at the Met Office, managing multiple international customers and collaborations. Okay, one of her main focus is working with critical sectors to help them understand the impacts of severe weather, space weather on their operations. And the title of the talk is Operational Space Weather Forecasting at the Met Office. Thank you, Krista.
Thank you, and thank you for the introduction, and thanks for the opportunity to speak here today. And what I'd love to do today is give you an introduction to space weather forecasting at the Met Office, why we do it, why it's important, how we do space weather forecasting, some really interesting new innovations that we've got coming through, and then a view to the future, where we're going, what new developments are there going to be. So when I say that I work in space weather forecasting, it is one of the lesser known areas of forecasting within the Met Office, but it is becoming increasingly critical. I do find if I'm speaking to anyone who's outside of the space sector, when I say I work in space weather, this is the way the conversation goes. I work in space weather. Oh, wow, that's so cool, space weather. What is space weather? And then it's my opportunity to try and grab their attention without making them run away too quickly. Space weather, of course, it describes changing conditions in space and is tends to be driven by activity on the sun. It is what causes the beautiful aurora, the northern lights, the southern lights in the southern hemisphere. But then it's trying to get across the importance of space weather. It's not just about pretty lights in the sky. There's real impacts which come from activity on the sun. So when we're looking at space weather forecasting, there are key areas that we're looking at. We've got solar flares, or solar radio bursts of electromagnetic energy from the sun, or solar noise, radio noise. This can impact on communication systems. So solar flares can cause disruptions to layers of the atmosphere, the ionosphere, which is critical for our communication systems, such as high-frequency communications, and it can cause interruptions to GNSS. This is of note to several industries who are reliant on these space-based technologies, particularly aviation, defence. Although, as Lucy highlighted in her talk in the keynote, there are so many different parts of society now which is reliant on space-based technology. You possibly don't even realise the reliance that they have and the disruptions which could be faced by space weather. Alongside solar flares, we've got solar radiation storms, something which has been quite topical recently. There's always a background level of radiation, so, galactic cosmic radiation, brought to us from distant galaxies. When we're looking at space weather, we're looking at eruptions of solar energetic particles, predominantly protons from the sun. We'll be looking out for these following on from a solar flare, looking at these high energy particles, which normally were protected from radiation through the Earth's atmosphere by the Earth's atmosphere. But when we have one of these events, we can see the radiation transferred down through the atmosphere to even affect us at ground level. Solar radiation storms can cause disruptions to satellite systems. It can cause disruptions with our communication systems. And in the extreme events where we get these ground level enhancements, we can see an increased radiation dose, which can lead to a dose of radiation at aviation altitudes for crew and passengers on aircraft, and disruptions to avionics. And finally, we're looking for coronal mass ejections leading to geomagnetic storms. This image here is a coronagraph. So it's a view of the sun with a shield over the camera lens where the sun is, so that we can just see the outermost layer of the sun, the corona. From here, we can see these enormous eruptions of charged plasma heading out into space. And if this direction is right or wrong, depending on your perspective, heading towards Earth. When these coronal mass ejections arrive at Earth, they interact with the Earth's upper atmosphere magnetic field, causing geomagnetic storms. Again, this can cause disruptions to a whole range of technologies that we're reliant on here on Earth. We can see disruptions to satellite orbits, disorientation from satellites. In these extreme events, when we get a big geomagnetic storm, we can have an introduction of ground-induced currents across the ground surface, which induces currents in the likes of power grids, pipelines, and so on. So space weather is occurring all the time, in the same way that our terrestrial weather happens all the time without impact, space weather is as well. But it's the big events which can cause real impacts to us here on Earth and disrupt the technological systems that we're reliant on. So that's what space weather is, and it's becoming increasingly important the more that we become reliant on these systems, as it can disrupt technology, communications, and infrastructure. So it's because of this reason that it's recognised as a risk to the UK, and space weather since 2011 has been recognised as a risk on the National Security Risk Assessment or National Risk Register. It is one of the top 10 risks to the UK. Just to put things in perspective here, if you're not familiar, the impact is on the y-axis and the likelihood on the x. So severe space weather is seen as a significant risk to the UK. Other space-based system disruption is also on there. So loss of PNT, again, in Lucy's talk, she talked about if we lose PNT, you're looking at £1 billion worth of losses for just one day. And there's also a disruption of space-based services and deliberate disruption there. So it's for these reasons that the Met Office has got a Met Office Space Weather Operations Centre, or MOSWOC, which is providing 24/7 forecasting of space weather and providing guidance to critical sectors so that they can mitigate against the worst of the space weather risk. So the Met Office has the delegated ownership of severe space weather. We've run these 24/7 operations since 2014, so just over a decade now of experience in space weather forecasting. We are a 24/7 expert staffed operational centre. All of our space weather forecasters are meteorologists who we then train up in space weather as well. So we've got experienced forecasters, this is the route that I took in, emergency response forecasting, used to responding quickly to a whole range of different threats. You learn about the space weather and you apply that knowledge so that you're able to apply the best advice with the information that you have. We're one of very few global guidance centres. In fact, it's probably just us and the Space Weather Prediction Centre in the US, staffed 24/7, 365, providing guidance across a range of sectors for the entire world. We also have operational coordination between international centres, so the Space Weather Prediction Centre in the US, the Bureau of Meteorology in Australia. Our forecasters have got constant communication with the different forecasting centres. If we're expecting a significant space weather event, we'll be seeing what they're thinking too. It helps to compare our thoughts, to consider what we think the worst case is going to be, and just have that sort of this understanding. When space weather impacts, it impacts large areas. It doesn't respect geographical borders. So when we have a significant space weather event, we need to be all working together. We're a national capability supporting a range of sectors. So that includes the government, the military, critical national infrastructure, as well as providing information for the public. So I'll go into a little bit into our forecasting process and how we actually forecast space weather. It's somewhat different to how we forecast meteorology, it's fair to say. This is what our forecaster client looks like. It is a dashboard which brings together all the information our forecasters will need to be able to be analysing the sun, assess where there's potentially a problem, and then issue alerts, warnings, watches, forecasts. We're reliant on satellite imagery. In this case, we have 2 coronagraph images there on the sun. This is just from a couple of days ago. And then looking at the sun in different wavelengths, we can also see different features, whether that's solar flares, coronal holes, or the magnetic structure of the sun. And we can, from that, build an understanding of where the risks are in the coming days. We also have a range of sensors and ground-based, whether that's space-based or ground-based. So we have measurements of the solar wind there, and then some magnetometer readings as well, so we can see what the response is on the ground. We also have a range of forecasting models. I'm going to go into one of them in a little bit more detail in the next slide. What we've got seen there is the solar wind model and also D-region absorption model as well to understand the response of the ionosphere to solar flares. But really, what does that all mean? What are our forecasters looking at when they come on shift? First off, our indication that we could be getting significant space weather is sunspot analysis. The majority of impactful space weather originates from sunspots. So the first thing that we'll be doing is analysing visible sunspots. We're looking at the size, the complexity, how they've developed over the previous couple of days, the magnetic complexity of them as well. The sunspot region I've got on the screen there is from May 2024, which produced one of the largest geomagnetic storms that we've seen in 20 years. That's 15 times the size of the Earth, just for a sense of perspective. From that, we can then look and see, from that we can give a potential of seeing solar flares using a bit of statistical analysis, how have similar sunspots performed in the past. We can give an indication then that we can expect solar flares. It's very hard to indicate the magnitude of the solar flare at this stage. Then we're just looking out for signs of action. We can see solar flares quite clearly in satellite images. And then following on from them, we're looking for radiation storms or coronal mass ejections, such as the one which is shown in the satellite image there, which I think is from October last year. When we're looking at these satellite images of coronal mass ejections, we can then analyse them. We can establish using a set of software where the CME has originated from, how fast it's going, and how wide it is as a CME. This is relevant because then once we have these parameters, we can put that into a computer model which we have, which is NLO. And what this is, it is a forecasting model of the solar wind. So in the centre of the circles there is the sun. Just to the right-hand side, there's a small dot, that's the Earth. And the spiral coming out from the sun is the solar wind. And then what we can also see is that there are these eruptions from the centre of the circle, so the sun, which is a coronal mass ejection leaving the sun. This gives an indication of arrival time at Earth and if it is in fact going to hit Earth. Once we have this, we can give a warning, we can produce our forecasts, series of alerts, warnings and watches to critical sectors to give this heads up that we're expecting a significant space weather event. We're increasingly moving to impact-based forecasting, highlighting to critical industries where they're expecting to see space weather and whether it's going to impact on them. And then we can also input this into models which give an indication of where the aurora is going to be, which is nice as a public outreach activity to say that you've got a potential for seeing the aurora tonight, but again, also can indicate that there could be communications problems underneath that auroral oval. That's where we are at the moment, but we've got a lot of really interesting developments which have been coming through within the last couple of years and things to look forward to in the future. We've got a R2O2R Research to Operations to Research programme known as SWIMMER, the Space Weather Innovation Measurement, Modelling and Risk programme. This is UKRI funded programme of work which started in 2019 and came to a conclusion a year ago. And what this did was identified gaps in MOSWOC capabilities. And then through a series of projects which were put out to academic partners and industry, looked to bridge these gaps in our forecasting. As Sarah said in her introduction this morning, there's over 40 partners which were involved in SWIMMER, so I'm not going to be able to touch on absolutely everybody who has contributed to SWIMMER, but here are just some of the some of the key models which we've got coming through first. So these projects were managed by RAL Space and the National Environment Research Council, NERC, and we've got some really great advancements coming through with our forecasting. The first one there on the top left-hand side with the map of the UK is a GIC model. So during significant space weather events, when we have a geomagnetic storm, this can highlight at substation level where we're likely to see the biggest ground-induced currents in the energy network. So it's providing a nowcast and a risk forecast of where we're likely to see impacts. Below that, we've got a radiation belt model, which has been developed by the British Antarctic Survey. And this gives an electron forecast, nowcast, for geostationary orbit and the slot region. That image there is, again, from the May 2024 storm, where we can see there was a compression of the slot region, with an intention in the future for that to come down to lower orbits as well. On the top right-hand side, there's an output from the Aeneas model, developed by the University of Birmingham and other partners. This is a groundbreaking ionospheric and thermospheric model which uses data assimilation. And the outputs will give a whole range of different models, different outputs to indicate risks to the thermosphere, which is relevant, of course, for satellite drag, and the ionosphere, which can impact on HF comms, GNSS. The image which you've got there is showing total electron count, so it shows where there is the risks of disruptions to GNSS. And then below that, there's the Mary Plus model developed by the University of Surrey, and it shows the risk of atmospheric radiation. As well as models, we've got some brand new recent developments leading on from those atmospheric radiation. Your model is only good as the observations which are verifying those models. We now have some neutron monitors which have been installed at ground level in Lerwick and in Camborne, and also the radiation monitors which have been developed for use on board aircraft and also on weather balloons on radiosondes. So we've recently launched a couple of these balloons. One of them was during an event a couple of weeks ago when we had the largest ground level enhancement in almost 20 years. And we were able to get balloons into the air within an hour of the onset of the radiation event. And this is brand new, innovative measurements which should really help to prove that our models are working as well as we could. Nobody else in the world is able to launch as quickly as we are into a radiation event to be able to understand the radiation environment whilst a radiation storm is occurring. And finally, as I'm running out of time, it's a look to the future and where are we going with space weather forecasting. One of the key areas is going to be these multiple viewpoints of the sun from the Earth. As it is, most of our space weather observations, in fact, almost all of them, are on the Sun-Earth line. The ones which are at L1, we've got SOHO, Aging Instrument, NASA and ESA owned. There's ACE and Discover, which is due to be decommissioned next year and replaced by the SWIFO Space Weather Follow-on L1 mission, which has been launched and is due to become operational early next year. We have this one viewpoint of the sun. This means we're seeing something in one angle. When it comes to coronal mass ejection forecasting, it's very hard to tell when you see an image like this. Is it a narrow, fast CME? Is it a wide, slow one? When's it going to get here? Our models could be improved enormously, our forecasting, if we have multi-viewpoints of the sun, particularly in the L5 position. So visual is going to be a real step forward for this. We'll be seeing active regions before they rotate that round onto the Earth-facing side of the sun, giving us an indication that we've got something significant coming up. And then when we have a coronal mass ejection, we'll be able to very quickly identify that it's Earth-directed, and it will improve our arrival forecast time at Earth. L4 would also be another position which would be helpful for when we're looking at these solar energetic particle events which are occurring. But Vigil, the mission to L5, has its funding secured at the ESA Council of Ministers last week. So we've had a lot happening in the last 11 years of operational forecasting at the Met Office. There's been a whole lot of developments within the science and the research community. And we're just coming out of solar maximum as well. But that doesn't mean that we take our foot off the gas. Really, if anything, we're just getting started. Thank you very much.
Thank you very much, and thank you for keeping us safe. Okay, so very important. Any questions? Yes. We have a couple over there, yeah.
Thanks for the talk, much appreciated. When we started worrying about space weather sort of 15 years ago or something, it led to MOSWAC. The Carrington event was the big bogeyman. Now we seem to know about these Miyake events that have occurred a few times in our past, and nobody knows how often they happen. Is there modelling of the effect of a Miyake event on our society that anybody in the UK is doing? It's probably not you, but is it happening somewhere? Or can anybody in the audience tell me? Thanks.
Probably one for other people in the audience, actually, from the research side of things, if they're aware of it. From an operational side, one thing which I'm noticing is that whilst the reasonable worst case scenario, the Carrington event, is what we prepare for on a national level as a reasonable worst case scenario, how we should, the biggest impact to the UK. It's not taking those big extreme events to actually be causing impacts. And the more that our technology is evolving and the more that we're relying on precision in our technology, even the lesser space weather events to some sectors would still be impactful. I would be interested if there is anybody who's got a thought about the Miyake event itself.
I don't think we're aware of what we're doing yet.
Okay. I think we do have another question, at least two. Yeah.
A possibly naive question, which I hope will have an interesting answer. How far in advance can you predict space weather, and how do you do that?
Excellent question. So it really depends on what we're looking at. So solar flares, when we're doing sunspot analysis, we can give a probability that we're going to see a solar flare, but we're not really able to do too much more than that. It's still an evolving science. Radiation events are similar. In fact, if anything, they're more difficult to predict. Not every flare leads to a solar radiation event, and we still don't quite understand why some flares cause radiation storms and some don't. When it comes to coronal mass ejections, once we see them leaving the sun, it depends on the speed of the CME as to when it's going to arrive at Earth, and that's when we can actually give a heads up that we're going to be experiencing impacts. So the fastest CMEs we would expect to be here in somewhere between 14 to 16 hours. The slower ones take a couple of days to arrive. Coronal mass ejections are the most impactful type of space weather, so it helps that we've got that heads up, but typically the faster that they're travelling, the higher the impacts will be.
Thank you. Yeah, another question over there?
So how big is MOSWAC and how often are you issuing alerts?
Ooh, how big is MOSWAC? The staffing is we have about 15 forecasters who are qualified in space weather, but they are dual trained with the emergency response bench. So at any one time, there's one space weather forecaster dedicated to space weather on shift, and there's at least one other who's working a meteorological shift as well. On top of that, we've got research to operations scientists, development teams, and business development like me. How often we issue alerts, warnings, watches? We have routine forecasts that we issue every day. So we issue a bulletin at midday, midnight, giving an overview of space weather and a forecast for the next 4 days. And then when it comes to how often we issue alerts and warnings, that really varies depending on the space weather situation. Now that we're at solar maximum, we are, as expected, seeing an increase in the number of alerts, warnings and watches which are issued. When it comes to the forecasts for the more significant types of space weather, though, that's not so frequently. So I would say in the last couple of years, again, we're at solar maximum, we'd expect to be this. There's maybe been, say, 3 events which we've been flagging at a higher level that this is one to watch. This could be causing more widespread impacts.
Thanks.
All right, thank you. I think we need to move to the next talk. You can ask any questions during the next break, okay? So thank you again, Krista. Okay.